ahead and introduce you, and then we'll start. Very good. So it is our pleasure today to have Michael J. Biercuk with us today. Michael is the CEO and founder of QControl and a professor of quantum physics and quantum technology at the University of Sydney in Australia. Michael earned his undergraduate degree from the University of Pennsylvania and his master's and PhD degrees from Harvard University. He held a research fellowship in the Ion Storage Group at NIST Boulder and has served as a full-time technical consultant to DARPA. Michael is a prolific speaker and a multi-time Australian Museum Eureka Prize nominee winner. It's our pleasure to have him here today on the AQT Colloquium. And the title of his talk today is Improving QC Performance with Machine Learning. So over to you, Michael.
Great. Well, thank you all for attending. Thank you first, Irfan and Sarah, for helping to organize. It really is a pleasure to get to speak with all of you today. I'll give an overview of some of the work that we've been doing at QControl. I'll just be clear that the work I'm presenting today is separate from my academic team, which is focused on trapped ion quantum computing. But here we'll talk about the work that we've been doing specifically with a focus on superconducting quantum computers and the application of classical machine learning techniques to drive performance improvements. And everything that we'll tell you about today is captured in the kind of software that we build called Boulder Opal. The outline for the talk is pretty stock standard here. I'll give you a bit of an overview into QControl. So I know many of you know us, but I just wanted to introduce the company in a couple of minutes. And then I'll talk about the specific control tasks that we're interested in undertaking in quantum computing. I'll then move on to experiments that we've done on IBM's hardware, both using what's called model-based robust control, so designing new quantum logic operations based on a Hamiltonian model, and then some newer results on universal gate set design with reinforcement learning executed in runtime. So that is hardware closed loop feedback in order to use reinforcement learning algorithms to design new gate sets. And then I'll tell you a little bit, if there's time at the end, about some of the exciting things that are coming outside of the quantum computing space, applying quantum control in quantum sensing. Now, I know some of you have seen this before, certainly Irfan and poor David, you've seen this before. But I think that the story is one that I wanted to just get across who QControl is. QControl is a company that I founded in late 2017, based in large part on the work that I had done, but of course with insights from many research teams around the world, from John's team, from Irfan's team, taking the perspective that in every major industrial revolution, we've seen that control engineering has been really one of the key enablers. We saw it with the invention of flight, with the Wright brothers introducing deformable airfoils and giving command of the shape of the wing to the pilot. We see it today with walking robots and autonomous vehicles and drone technology. And QControl is excited to be doing the same thing now, trying to help enable the emerging quantum technology industry by serving customers across different sectors. Now, what we build is technology agnostic. So we build infrastructure software that helps improve the performance of quantum hardware. And without doing the advertorial here, I'll just say, we service a wide variety of technical platforms in different application areas, but the results that I'll tell you about today are specifically focused on superconducting circuits for quantum computing. And we do have the pleasure of having a wide variety of organizations as customers and partners, including, of course, the AQT at Berkeley. And we're very pleased that we get to share with you some of these results today. But I think, as everybody knows, the most important thing here, which is an upfront acknowledgement of the work that's going to be presented, is the team. QControl is very proud to have the world's largest collection of PhD-level quantum control engineers, people who have specialized expertise in applying control to quantum systems. They come from backgrounds in quantum physics, in robotic control, and the like. I think this is a little out of date. We have a couple of people who've joined recently, but there is always one empty spot here because we are constantly recruiting. And if anybody's interested at the end, please do reach out to me. I'll just point out that today's work is predominantly led by Andre Carvalho and Yuval Baum. I can't see where Yuval is on this chart right now. There he is. But because we're a company as opposed to a public sector research organization, we also have a huge emphasis on making useful products. And so our team has a nearly equal weight of people who are professional software engineers, professional developers, user interface designers, and the like, trying to make all of our tools and capabilities in quantum control as accessible as possible for the broader population. So, well, thank you for indulging me as I gave that brief introduction. What I'm really interested in telling you about is, of course, the fact that we have some problems in the quantum computing space. Now, I appreciate that this is a colloquium, so I've tried to give a little bit of a broad introduction, but I also appreciate it's a quantum information colloquium, so I'm not going to go too base level. Everybody, I believe, on the call is familiar with the idea that quantum systems are prone to error. That over time, the information that we encode into a quantum device, whether it's a superconducting circuit or a trapped atom, is randomized by interaction with the environment. And this is something that can be a sight to behold when you think about it in the right terms and air quotes, which is to compare against error rates that we see in conventional electronics and conventional microprocessors. So as astounding as it is, if you convert into errors per unit time from the standard literature, a transistor in a conventional machine will run for about 1 billion years at 1 billion operations per second and never be likely to suffer a hardware fault. If you get the blue screen of death, it's because of a software bug. It's almost never because of a hardware fault. And of course, it's a bit of a community average, and everybody can argue about the details, but it's more like 1/1000th of a second as the relevant lifetime in a quantum computer. And this gap of, say, 24 to 27 orders of magnitude, depending on exactly how you count, is exactly what has been the dominant driver of R&D in the field, but also is the raison d'etre for QControl. We're interested in helping to reduce hardware error in quantum computers by deploying quantum control. Now, we do this by building tools that help engineer something that we call the quantum firmware layer. So this is the lowest layer of the quantum computing stack, just above the hardware. So the physical hardware is down at the bottom, at the top of the stack. And of course, everybody has their own version of this, which varies in the details. But at the top, you have user interfaces. And as you go down into the stack, you see that you're reducing the abstraction. You go from the operating system or quantum cloud services down to applications and algorithms, compilation, quantum error correction, et cetera. We're talking about the lowest level of the software stack, which is where software meets the underlying hardware. There are a couple of different objectives here, right? And the ones that we're interested in are, first of all, learning about what's in the hardware. So this is hardware characterization, or in control engineering parlance, it's called system identification, where you may want to characterize noise in the system, characterize Hamiltonian terms, do parameter estimation on your hardware. And there's a wide range of capabilities that come from control engineering that are relevant here. The next and another important one is building autonomy in these systems. If we want physical hardware that connects to higher levels of abstraction, we need it to run without constant human intervention. And so building autonomy is a key driver in making an abstraction layer in software. Then the last bit that I'll talk about today, at least, is in building error-robust quantum logic. If our interest is in making quantum computers that perform better, that are resilient against decoherence or general errors that come from control operations, then attacking this problem by the development of error-robust quantum logic is a key driver. So in today's talk, I'm going to be focusing on two aspects of what goes on in this quantum firmware layer. The first is error-robust quantum logic using something called open-loop control being familiar to anybody who comes from an NMR or MR background, and also automated closed-loop gate optimization. So using machine learning agents to autonomously design new gates. Now, in both cases, it's always ML, machine learning, that we're employing in order to undertake the key tasks that we're tackling. If you want to learn a little bit more about this, this idea of quantum firmware and the quantum computing stack was one of the cover stories for the March 2020 edition of Physics Today. Though it is not brand compliant with QControl colors, they did a very nice job making some beautiful artwork for the companion article. So what are we? Okay, so let's get into the meat of where we're trying to go. We know that all quantum algorithms are composed of quantum logic operations performed on qubits. This is, I think, not a surprise to anybody in this call. And we also know that those quantum logic operations are composed of physical manipulation of the underlying hardware, right? So sometimes the quote is that information is physical. When we have to manipulate this hardware, we obviously do so in a way that tries to affect a desired mathematical transformation. For instance, X represents a quantum mechanical bit flip on a qubit. Z is a quantum mechanical phase flip. The approach that we undertake in this, this one part of quantum firmware that I'll talk about today is to replace those individual logic operations with new definitions that give us the same mathematical transformation, but now do so in a way that is also resilient against error, right? So here's a little bit more of a detailed description of this process. Our desire is to take our total system Hamiltonian, which involves control. So this is what we're doing to our system. So some drive in superconducting qubits, this is the microwave signal that you'll be applying. And we also have some noise terms. And those noise terms can take various forms. We write them in a parametric way here, where we have a time-varying semi-classical variable, or classical variable, it's a semi-classical noise field, and a noise operator, where the noise operator can be a dephasing type Hamiltonian term. It can be an amplitude over rotation error. There's actually a very wide range of these error terms that can appear in a d-dimensional Hilbert space. But our task is to try to choose a control that, as much as possible, cancels out the dominant noise terms, right? So this is the task. And you can see a very, very simple example of this in the small animation here, where what we're doing is we're driving from the North Pole to the South Pole. That's a quantum mechanical bit flip. And we want to do so now in a way that is resilient against error. So by redefining the waveform, instead of just doing a square pulse, we're actually going to modulate the phase of this pulse. This is the phase of the microwaves. When we do this, we of course go from the North Pole to the South Pole, but you see we take some slightly different trajectory that involves exploiting, in this case, the symmetry of the Hilbert space, that being the SU2 surface, the qubit space. So ultimately what we're doing is we're redefining this waveform in such a way that we cancel out what's known as the error operator. In what follows, we'll always be defining our complex drive in terms of these two parameters, I and Q. So if you come from a microwave engineering background, this will be familiar of like IQ modulation. This is a nice decomposition that allows us to define arbitrary modulation of amplitude and frequency or phase of a control. How do we get that? Well, we know that there's a huge amount of literature that comes from the MR background on how to analytically exploit these symmetries in order to come up with robust solutions. Things like BB1 and Corpse are very famous examples. But what we've been working on, and what others have been working on, is the application of machine learning techniques to derive new numeric approaches that can achieve the same things, but with greater efficiency. And generally, it involves improving the efficiency of how long it takes to perform an operation with a certain degree of robustness. The approach that we've taken in order to make this an efficiently solvable problem with machine learning tools is to adopt a programming framework called a Dataflow graph. So this is an approach to performing constrained optimization, which is extremely efficient and gives us some huge benefits. Now, I'll happily talk you through the key aspects of this. You don't have to read all the detailed text. But the idea is that when we have an optimization problem, here we want to, for instance, minimize a noise term by modulating our control signal. We can encode that into nodes of a graph. Those nodes involve what is the target operation we seek, what is the objective function we wish to minimize. So it's some cost function that we define that can be fed into a machine learning algorithm. What are the control knobs that we have available to us? These are the accessible classical controls. And then we can also add things like what is the noise and disturbance we wish to minimize. So I do want to emphasize at this point, we're talking specifically about something, you've seen this word a couple of times, robust control. This is not optimal control in the sense that we are not just trying to find the shortest path between 2 points in a d-dimensional space. We're trying to find a path that is resilient against the noise terms, the fluctuations on the uncertainty that we have in our system. All of them are captured by this node in a graph. But then we can also add constraints like smoothing to meet band limits in transmission lines of a Dilfridge, constraints like time symmetry, like temporal discretization, as you might face when using an arbitrary waveform generator, which has some sample rate. Every single one of these can be efficiently mapped to a simple node in this graph. And then all one has to do is identify which node corresponds to say the cost that we care about in optimization, and which is the output. Now, this is a really efficient way to encode this problem, because, well, in part because it allows us to leverage a wide range of machine learning tools that come from a package called TensorFlow, which was originally built by Google. This is a fantastic package for this because it allows for what's called automated differentiation. So for anybody who's familiar with this field of optimal or robust control, you know that calculating the difference or the gradient between solution A and solution B is a very difficult part. And here we're able to use some well-established machine learning packages in order to tackle this problem just by framing the problem in the right way with these data flow graphs. This does give some really huge benefits, and we see them in time to solution for different classes of optimization problems. Now, I'm just going to focus on the graph at the right here. These are two different proxy benchmark comparisons. But what we're comparing is the time to solution to run some number of optimizations over the dimensionality of a Hilbert space. So it's how many qubits, how many two-level systems are connected together in this optimization. And the different lines correspond to a conventional NumPy-based optimization, QTIP, which is a very well-known package, and then the QControl Dataflow graph approach, both local in magenta here, that's this curve, and then in purple, another approach, which I'll tell you about in just a second. Now, the important thing is that even when you run the local code, the data flow graphs give some advantages because the automated differentiation in TensorFlow is so efficient. But another thing that we had worked on in designing these techniques is something you might call HPC as a service, high performance computing as a service. That most of us don't have a sysadmin who is able to manage a cluster for us full time. And because of that, and the fact that cloud infrastructure resources are ubiquitous and extremely low cost, we had worked on building back-end infrastructure to allow you to just call what is effectively high-performance computing resources that we make as virtual machines. And so there are, in this case, virtual machines that have automated GPU transition, and you gain like an order of magnitude in time to solution by leveraging this cloud parallelization. But all you've done is you've executed Python code, right? So we found that this has been very efficient for helping us come up with some more complex solutions for harder problems. Now to the experiments. We're going to take these tools, these capabilities in TensorFlow-based optimization. We're going to take a model of a system. In this case, it's a qubit with leakage that is extant on the IBM hardware, and we're going to replace the driven operations, the gate operations, with new definitions that emerge from our machine learning toolkit. Now, we're going to do this for both single qubit gates and 2 qubit gates. I'm going to start with single qubit gates. I'm going to then talk about execution via a framework called Qiskit Pulse. So this is something that IBM offers that allows analog layer programming of the underlying hardware. So the analog layer means you can change the shape of the waveform instead of just applying an X or a Z as you could in the conventional Qiskit approach. And just to answer a question that I see that came up in the chat, HPC is high performance computing, Claire. So now remember,
so Mike, I understand that HPC is high performance computing. What do you consider high performance computing? Is that like Summit at Oak Ridge, or is that a smaller machine that has similar characteristics?
Oh, I mean, so no, it's HPC-like. So, so the first thing is, it is completely arbitrary what somebody asked for, right? The amount of computing resource is effectively infinite from AWS. The performance that we offer as stock is like 26 core, I think, CPUs that service the optimizations that we perform with GPUs, but that can be spun up to effectively anything. I think HPC didn't fit on the line, so I think that was I want to emphasize this is more like cluster or workstation as the conventional approach, but it can be scaled to whatever you like. Okay, so remember, we're going to be defining these new gates. We're going to execute them in Qiskit Pulse. There are different ways you can do this. What I'll show you today is going to be focused on something called the U3 decomposition for single qubit gates, where here the objective is to use a standard decomposition that only involves a driven pi/2 pulse. So it's the driven, rotation from the North Pole to the equatorial plane plus virtual Z gates. And with this structure, you can get to any arbitrary rotation on the Bloch sphere, right? So that's the basis. And we're going to optimize those pi/2 pulses. That's what we'll start with. So here's a simple example. How does robust control work? We start with a optimized pulse, which comes from our machine learning optimizer. It has a couple of constraints that are applied. So there's a sync smoothing filter to meet bandwidth limits on the IBM hardware. There is a return to zero condition, and then we enforce time symmetry for simplicity here. When we measure what is the error of the rotation as a function of an applied detuning, where the center corresponds to zero detuning, then what we see is that as expected from like the modified Rabi rate, when you take the conventional default, when you have a detuning, that you get an incomplete rotation. This is manifested as an error. So that's not a surprise at all. But as you move away here with the QControl robust pulse, you see that you stay low at the measurement fidelity floor over a wide range of parameters. So this is an example of robust control. Now I want to emphasize, anybody who's come from the MR background, this is an extremely familiar type of graph, right? The important thing here is that we achieve robustness in both quadratures, both detuning and amplitude, with 5 times shorter pulses than you would need if you did a concatenated C in BB or corpse in BB1 or another analytic prescription like that. So now this is based on engineering an error. We apply an error to test and demonstrate that this is robust. This is what happens when we apply these in the real hardware under native conditions. The colored lines here correspond to 3 different model-based robust gates that we've built. The black is always the default drag pulse applied in the IBM hardware, and then the x-axis is the number of pulses. So as you apply more pulses, the fidelity decays as you would expect, but in all cases, the fidelity decay is more rapid with the standard default. Indicative of the fact that we're engineering robustness in these model-based optimized control solutions. These 5 different graphs correspond to 5 different qubits on a device called Valencia. Now we can parametrically fit with an over-rotation error and an incoherent decay. Gives us very good agreement with the data. This is the model that Will Oliver had published some time ago. And then with this, we extract in quadrature an overall error per operation, which is shown on this graph here. So the error per operation is larger, obviously, with the default gates than with the QControl robust pulses. But there are some other benefits as well. The first is that the spread of outcomes over devices is reduced by approximately an order of magnitude. So what we see is that fabrication variances can be mitigated by controls defined using machine learning. Now there's another benefit that's pretty cool. So here, what I'm showing is the same thing, except as a color scale. Error per gate as a color scale, bright is high error, dark is low error. The gates executed here are for the IBM default, and then we have 2 of the 3 that I showed you on the last slide. The amplitude robust, that's robust to over rotation errors, and dephasing robust against frequency offset errors. I think the first thing is obviously the error rates are lower. That's great. The error homogeneity is improved by 10x over the device. But then here's something else. This is the cool bit. For the IBM default gates, we have to, well, the system is recalibrated every day. In fact, it's usually twice a day. So every 12 hours, they recalibrate the definition of the pulses. This is what I do in my academic lab too. It's pretty standard. With these graphs on the right, we haven't recalibrated anything, right? We define the gate, in this case on August 3rd, and we just run exactly the same waveform every day. And on every day, it's still approximate up to an order of magnitude better than the default gate that had been calibrated that day. This is a manifestation of robustness against drifts in the hardware. And the dominant drift that we saw when we were characterizing the hardware was drifts in the I and Q calibration of the microwaves that were applied to drive these gates. There are some other cute things here, like these gates are all applied in parallel. So the role of crosstalk is mitigated as well with these gates. And so I'm happy to talk more about that with anybody who's interested. But this was the first demonstration that these machine learning derived gates can give some pretty substantial benefits in real hardware under native conditions. The next part of this story comes from moving from open loop model-based control towards greater automation. Remember, I told you automation was one of the key things we wanted to achieve in this quantum firmware layer. Now we're going to do this with various forms of closed loop control. So this is based on closed loop. Excuse me, I should say this is based on projective measurements. So it's a little different than the closed loop control that say Irfan's team has worked on, where there were, for instance, weak measurements. This is projective measurement on the qubit, where the measurement result is fed into an agent that decides what control will then be executed on the experiment. So this is entirely autonomous within the hardware. There are different ways that you can connect this with, your own custom code, or we use a package called mloop, which is a nice data package, or data management package. And then there's a wide range of agents available for this that we've tested. And I'll tell you about results with 2 of these, simulated annealing and reinforcement learning. One thing that we did that we felt was important when accessing these cloud systems is enable and test agents that worked well with batched data collection. So what we mean here is, if you don't have the benefit of your own, superconducting or general quantum computer, you'll often be limited by the API that calls or executes commands on the hardware. We are familiar with the fact that across all the different platforms, the API calls to the hardware are the dominant temporal bottleneck. That's the slowest part of the step by more than an order of magnitude. And so if we had to make a call for one experiment and then wait, we could wait seconds or even minutes for one data point to come back. And so we built a closed loop optimization package that was happy to accept batches. So different parameters, different test point, and then cost evaluations that would all then be fed to the agent at the same time. So in one API call, the agent would then process them as a batch and decide what to do as the next set of measurements. So this was very important for us in reducing the latency of closed loop optimization in this hardware. So let me show you, first, one very, very straightforward application of this. With our single qubit model-based robust pulses, we have an I and a Q quadrature. We are defining the 2 different components of this waveform that give us the desired operation. Actually implementing these successfully requires calibration of I and Q. So we have to know what is the overall scaling of the pulse to get a particular Rabi rate, because I and Q are mathematically the Rabi rates. AI and AQ are the programmed voltages on the hardware. Sorry for the background noise. And then we also need to know what is the relative balance or imbalance of the I and the Q channels given by this SREL parameter. So what we did was ask, so originally we did this by some scripting where we would scan over these parameters, and then find a peak in a curve and what's kind of like a fringe. Instead, in this case, we asked the automated optimizer to do this for us. And with 4 batched experiments, which took, of order a few seconds, we were able to, a few minutes, we were able to find the optimal parameters for both the amplitude overall scaling and then the relative scaling that we could then use to implement the highest fidelity gates, right? So it's a nice step towards automation, but that's not very impressive. Frankly, it's just, it's a little cute. Where these automation techniques really start to become powerful is when you can use machine learning agents to find information that is not really easily accessible to you. When you move from single qubits to multi-qubit gates, the biggest challenge, of course, is that often there are either unexpected or unknown Hamiltonian terms. Sometimes those Hamiltonian terms are transient. So in this particular case, we're, of course, designing some gate that we apply with an arbitrary waveform generator. It's programmed in Qiskit pulse. It's defined mathematically, it's programmed in Qiskit pulse, and then it goes to an arbitrary waveform generator, which sends signals through control lines, which then crosses the packaging to the chip, and of course, eventually reaches the quantum system. Now, in this case, everything inside here is a black box. We have no insight whatsoever into what IBM is doing. They don't inform us what AWG they use. They don't tell us anything about the bandwidth of the controls. In fact, they will not tell us. And so doing full characterization of the hardware is one approach, but of course, everybody knows it's quite inefficient as the system dimensionality increases. Another thing that you can observe is that if you take, for instance, the published model for a particular device, and you use the backend simulator to say, what is the evolution of, say, a 2-qubit subspace, but then you measure the same thing, there's pretty strong disagreement. So the dashed lines are the simulations from the IBM backend simulator using the published model for this Valencia device, Casablanca device, and then the dot points are experiments, and they effectively don't overlap at all. This is indicative of the fact that there are unknown or at least uncontrolled Hamiltonian terms.
Mike, as you know, we have a user program, and if you do something with us, we'll tell you absolutely everything you need to know about our devices.
Good. We're very happy to keep engaging more with you. Irfan and I have talked about that a little bit recently. This is, I think many people will encounter this kind of problem. And even in a system where there is a lot of information given, there are always surprises that crop up, right? So how do we deal with this? The approach that we've taken here is to employ reinforcement learning. And the experiments that will follow look at designing a universal gate set via AI agents, leveraging something called reinforcement learning. So this is, again, it's a form of closed loop optimization. It's closed loop in runtime, which means that the agent decides on a control to apply, applies that to the quantum computer, takes the measurement, and then makes its next decision of what to do, right? So this is not, I want to just distinguish, there have been other reinforcement learning approaches where you use reinforcement learning in a numerical setting, and then you take the outputs and then you test them and experiment. We're not doing that. We're treating the experiment, the environment, as a complete black box, and we are allowing the agent to discover new gate sets. Now, you'll see that there's an extra part of the loop here because reinforcement learning is a little bit different than general black box optimization. So how does this work? Well, the first thing is that reinforcement learning, again, unlike standard closed loop optimization or black box optimization, involves gaining intermediate insight to what controls do. Right. So this is a big distinction. You don't just apply a whole gate and ask, how good is my gate? You actually ask, what does each component of my gate do in time? And so that means that we have these things called steps, where a step, you can see there's the red that corresponds to the left and blue that corresponds to the right on the graph. The step involves choosing what's called action to take in one time slice of your gate. You're going to apply that, partially composed gate with some of the actions defined. You're going to measure, in this case, using a form of state tomography, what is the resultant state? Where does the single or 2-qubit state end up? And then you're going to iteratively build up a complete set of time slices to compose one complete gate. That complete gate is called an episode. Right, that's one candidate gate. But remember, you've measured these observables at each time slice, and of course, everything involves projective measurement, repreparation, and restarting the cycle multiple times. Every time we complete a full gate, we perform a measurement of fidelity as well. So that's our cost, or in the RL language, this is called the reward function. Right. And all of these measurements involve repetition, of course, to get statistics because of, the projective nature of measurements. And then we do a weighted average in our reward where we'll have designed a full gate. We'll then repeat that full gate different numbers of times, and typically up to about 40 times. And then we'll measure the decay or the reduction in fidelity. Now, this is designed to attack a couple of things. First is that measurement access is limited in this hardware, as we know. Spam in this particular hardware is pretty big. So the measurement error is a few percent, 3 to 5%. And of course, the spam can throw your reinforcement learning agent off if you're not careful. And then the last is we want to avoid pathologies that come when, for instance, you have different duty cycles that lead to different gate errors for different sequence lengths. You want gates that perform well when they're applied once or twice, as well as when they're applied 100 or 200 times. And so in our reward, we have a weighted average of the fidelity that comes from repeating the gate multiple times. How does it work? Let's start with a single qubit gate optimization. The IBM default drag pulse is shown here. And then I'll focus on panel C first. This is what the deep reinforcement learning agent comes up with as a single qubit gate when it is tasked with coming up with a gate that is both T1 limited and suppresses leakage. Now, there are some choices that are made here. For instance, we knew based on the published T1 that the IBM gate was only about 20, the fidelity measured by randomized benchmarking in the bottom here, which is, for those who are not familiar, this is just a proxy measure of how well a gate performs. It gives you average gate performance. The IBM default was only about 20% in terms of error away from what we knew was the T1, the incoherent floor. So we made a gate that was about 20% shorter and asked the deep reinforcement learning agent to find that. And lo and behold, it finds this wacky looking gate where we have no real insight into what's going on because the model that the agent builds using something called policy gradient is not human interpretable. It's only interpretable to the deep neural network itself. That gate, when we run it in randomized benchmarking, is about 20% better than the IBM default. And so that's because we're running right into this T1 limit. So that's really good, right? It says that the reinforcement learning agent can not only find a decent gate, but it can find a gate that outperforms at the limit set by incoherent processes. We can also go faster, right? So in this case, we asked the gate to, we asked the reinforcement learning agent to give us a gate that was about 3 times faster than the standard default. And it also finds a gate that outperforms the default. Now here, the outperformance is much more marginal. It's actually, it's within the margin of error. So we'll claim that they're approximately the same, right? But it's 3 times faster. And we have not suffered from a major degradation due to leakage errors. This comes from the fact that the reinforcement learning agent in its cost evaluation has a measure of how much population goes to the 2 state outside of the qubit subspace. And so the reinforcement learning agent knows when we have leakage processes and tries to minimize them. So cool, it works. The thing that was a bit surprising to us and was actually one of these happy surprises as opposed to the bad surprises we normally get in experimental quantum physics was that the gates that are derived using either this 28 nanosecond version or the 12 nanosecond version exhibit robustness against fluctuations. Now, we did not explicitly include robustness in our optimization reward function. Instead, the optimization, the training procedure for the deep reinforcement learning agent takes long enough that it crosses over the cycle of calibration on the IBM hardware. So you start training, in the middle they stop you, they do a calibration, and then you keep training. But obviously the system settings can change quite substantially as they perform this calibration, which is out of our control. And the learning agent had to discover robustness. It had to discover solutions that didn't change even when you would suffer this big calibration dislocation in your training process. So over here, approximately 2 weeks, we see that the deep reinforcement learning agent design gates perform within a band that's given by the fluctuations. Day to day, you always get this, approximately 20% improvement. The fluctuations here, the shape of those fluctuations in time matches pretty well the shape of fluctuations in the reported T1 in the device. So we don't measure that. We just take that from the back end. If I scaled these bars up, it's actually, it's a very close fit of that pattern. But we also see that we're close to the incoherent error limits that are derived from what we know to be T1. And you get similar performance in terms of robustness over here a week that we measured for the 12 nanosecond gates. I want to emphasize these gates don't get rescaled at all. It's just the exact same voltages that we program in the AWG every day in this test. But the exciting bit comes when we look at the 2-qubit gates, because we know these are the bottleneck in quantum computer performance. The single qubit gates are at the 99.9% or better level. The 2-qubit gates that we see in the hardware are typically at the 98% level. And I do want to differentiate here. There is the best achieved gate, and then there is the typical performance, right? So many teams will often quote the best achieved gate. which could be 99.5 or 99.9% fidelity, even for the 2-qubit case. But what we see across all the different hardware backends that we've studied, it's been about 6 of them, is that the typical performance is a couple of percent error, right? So these are what we want to attack. The particular gate that's used by IBM is something called the cross-resonance gate, where you apply a microwave tone to 1 qubit in a pair in order to shift its frequency to be near resonance with another qubit connected via a resonator. What can we do? Well, we can try, for instance, to suppress crosstalk errors. In the programming of the waveforms in the cross-resonance gate, IBM has to add some additional tones that cancel out classical crosstalk on other qubits outside of this pair, or even within the pair. We can look at simpler controls. We can look at building robustness to frequency and amplitude fluctuations that we know are present in this hardware. And we can look at potentially taking care of signal distortions that come when we apply this pulse of microwaves down the transmission lines. Here's the summary. We task the deep reinforcement learning agent to find 2-qubit gates where in this particular structure, so the black here is the IBM structure, there's a single qubit channel, so there are pi pulses here in an echo-like structure. There's the cross-resonance channel labeled U1, and then this other thing D1, which is a crosstalk cancellation tone. This is just to get rid of some classical crosstalk in their hardware. We take this overall structure and we ask the agent to redefine that segment of the cross-resonance interaction. When we do that, we get something that looks like what you see in panel C here on the right. So it's the same overall structure, but now you have some fluctuations. Those fluctuations are reasonably repeatable in different runs of the optimization. We don't know what physics exactly is being exploited here, but when we take this gate and we just apply it sequentially, different numbers of times, the decay in fidelity is reduced by 2.5 times or thereabouts. And the net error per gate that you extract is gives you a fidelity of about 99.5%. One thing you'll notice here is that this D1 line is set to 0. So we have no classical crosstalk cancellation. The structure of the gate in the programmable modulation of the cross-resonance interaction seems to compensate for the crosstalk that was otherwise present, right? But we don't use this channel anymore, which is quite neat. You can also see robustness in these gates. This was another happy surprise for us. The dotted lines here, again, you repeat the same gate, you measure the infidelity, black is the default, purple is what we optimized. Dotted lines are what we started with. It was measured like the day of the optimization or the day after. Black lines are 25 days later. So 25 days later, no additional recalibration of the purple pulses, of the deep reinforcement learning pulses, compared against that day's best calibration of the cross-resonance ZX minus pi over 2 rotation. And you see that you still outperform by more than a factor of 2. So this was pretty exciting for us. You see it in interleave randomized benchmarking. Also, the benefit is not quite as big. It's more like 30% or something, or 20%. And that's, we believe, in part because you compose this ZX minus pi over 2 with now imperfect single qubit rotations to give you the C0 gate. It also does work in swap. So we did the same kinds of experiments, repetition and interleave randomized benchmarking. We see about a 45% improvement in the swap gate. This, was related to the IBM Open Science Challenge, which we didn't enter, but we did the same task again with the deep reinforcement learning agent. So no human analytically defined gates, just asking the agent to find better swap. In this case, we've done both deep reinforcement learning of individual constituents and deep reinforcement learning of the constituents in situ inside this swap structure, and the performance is approximately the same. So now, in the last few minutes, the last 2 or 3 minutes, I wanted to tell you about something outside of quantum computing that we're very excited to be working on. All of our technology is relevant to quantum sensing as well as quantum computing. And we've been excitedly developing new techniques to apply control. All these machine learning techniques that are used here, that I've told you about to improve the performance of quantum computers, to bring them over into quantum sensors, and in particular, quantum sensors based on trapped atoms. Cold trapped atoms for atom interferometry. That's our particular focus, but we also service, of course, NV centers and all sorts of other technologies. If you look at some of the great literature in this community, one of my favorite papers is Rev Modern Physics from Christian Dagan and Paolo Capolaro about quantum sensing. It's a great simple title. They outline what are the general tasks that one uses in order to operate a quantum sensor. So you'll maybe initialize it, you'll change the state of your sensor, you'll allow it to evolve for time, you'll go back and you'll read out and you'll repeat an average, and then you'll make an estimate of the signal. Without being pejorative, I think the reality is that, in most, somebody will object, in most settings, the focus in quantum sensing research has been on improving the hardware, right? And for the most part, the operation has been generally the simplest thing you can do, generally, right? We see that as a huge opportunity to get more and more useful information out of quantum sensors. So in every single part of the operation of the quantum sensor, there is an opportunity for control to have a benefit. We have demonstrated 10x improvements in loading of atoms into traps using automated simulated annealing optimizers or Gaussian process optimizers. We've shown robust control improves atom interferometers. We know that you can do clever time series analysis to get better information out when you're doing signal estimation. Sorry, there's going to be some background noise because apparently it's raining very, very hard right now in my house. Where are we going with this? We see opportunities to build a new generation of space-based atom interferometers where we can do performance augmentation and reduction in size with fixed sensitivity by leveraging the benefits that come to us from control. We're building new technologies for tight swap atom interferometry, both in navigation and in geodesy, so measuring gravity in the globe. And we're very excited that we're contributing with a partner, Advanced Navigation, to navigation systems for maritime applications, making submarines that can navigate without GPS for very long periods of time, and bringing this technology to space exploration. So we have an engagement with the Australian Space Agency. We're part of a consortium called Seven Sisters, which is bringing, well, overall, it's part of a companion mission for NASA Artemis, which is to bring the first woman and another man to the moon. Our role is, in fact, bringing quantum sensing to lunar exploration as part of the first step towards the Mars supply chain mission. So it's a really exciting new area of activity for QControl focused on these quantum control enhanced sensing systems. So we have great opportunities in both Sydney and Los Angeles. If anybody on the call is interested, John, maybe it's time to come back to Sydney. We also now have an office in the EU. So we have an office in Berlin that we've just started hiring for. We're very excited to be expanding globally. I'll leave here. We've talked a little bit about QControl and quantum firmware, this low level in the quantum computational stack. We've talked about how we can use machine learning to design using Hamiltonian models, error-resilient quantum logic that outperforms the default by up to 10x on IBM's hardware. And we've shown how fully autonomous reinforcement learning agents can be used for gate set discovery. Now, we know that this is an area where there's been a lot of activity. Irfan's group has also used these kinds of learning techniques in state prep. This is, we think, the first time it's been done for a universal gate set tune-up. And we've told you a little bit about the future work that we're undertaking as we expand into quantum sensing. So please, if you're interested, please get in touch and look forward to your questions. So thanks very much for your attention.
Okay, thank you, Mike. Let's clap for our speaker. Great talk.
So
I'd like
Mike,
with that.
I would like to push you